Now let's recall that what we want to do, we want to define the integral for functions which are non-negative and measurable. So they are measurable with respect to the Borel sigma algebra and the abstract sigma algebra S. And this is the Lebesgue way to do it. So the definition is that the integral now plus is emphasizing that we are now looking at the new integral in principle, the integral of positive functions. And the definition is as supremum of these simple integrals of g in a space of functions dominated by f. So let's say df is the set of simple functions which are where f is dominating them. So this way. And well, we know that everything is non-negative, so we could include 0 there as well. Okay, that's our new definition. And we will study if it makes sense. Does it make sense? Every g belongs to it's a simple function, so we have defined this as a number. This has been defined as a number between 0 and infinity, including infinity. Then we have numbers here. We take the supremum, that is the least upper bound. So the least upper bound of numbers between 0 and infinity is also a number between 0 and infinity. So that's why we can know that this total supremum is a well-defined number between 0 and infinity. If you look at this supremum, it's the least upper bound of all simple functions in the world, where f is dominating. So it is not at all a simple thing to compute, actually. So think about implementing this with MATLAB. Sounds quite a challenge. But let's worry about that later. We will come back to that, how to compute these in practice. Now we know that it's a well-defined number on the non-negative extended real line. And what else do we want to know? Now we have two different integrals. We have this box integral and this plus integral. So the first fact is a kind of extension. Let's prove this extension fact. So the claim is that if we take the new extended kind of new integral concept and we apply it to a simple function, so if f happens to be itself a simple function, so then this should be the same. Why is this true? Why is the extension property true? Well, let's do two phases. First of all, if f itself is a simple function, so then f belongs to this collection of functions where f is dominating. F dominates itself trivially, of course, when f itself is simple. So that's why, if you look at this definition, how we did it, this was the supremum of all functions in df. And then we look at this simple integral. Now the supremum of all functions, because f belongs to this class itself, so then this supremum is of course bigger. If you only look at the single f here. And that's one part of the proof. The second part of the proof, how to do that one. So now we have done this inequality here. then we will reverse the inequality in part 2. How do we do this one? Let's take, think about some function g in this df. So if it's there, so then we know that g is at most f. And now in this case, g is a simple function, f is a simple function. So we use this monotonicity property that we proved in the previous hour, that we know that, okay, monotonicity is true for these simple integrals. So then we know that these simple integrals are ordered. Yep. And now we know that, okay, this is true for all g in this df. Yeah. So especially if we take the supremum of all g, so then it follows that then the integral of the new integral, which is defined as the supremum of all g in this function set, because every one of these is bounded by, so then the least upper bound is of course also less than this one. So and if you compare this, so you know that this is now the other direction, and we have done that now. So that's the end of the proof. The extension was a simple thing to do. We know that this new integral coincides with the simple integral when f happens to be simple. But on the other hand, this integral is now with this supremum defined on a really, really big space of functions. Think about that. This is a huge class of functions actually. For example, yeah, think about if S happens to be the real line, this would be the all Borel functions which are non-negative. So it's a really, really big class.